Yeah, okay, thank you. Alright, so good afternoon everyone. So today we start we are still on the first part of the book and I don't think we'll get much beyond that in this semester. But we do start a sort of new flavor of things for the next couple of chapters. So it's going to be much more geometric, which also makes it more challenging for me because it's not my usual space of operation. Yeah, okay. So we'll start talking about the perfect matching polytope in particular. But before that, let's just go through some basics. Yeah, I actually had to prepare notes today. Right. So the edge space of a graph is the set of all real valued functions on the edge set of the graph. So you can think of it as a labeling of the edges using real numbers. Right? Every element of this may be viewed as a labeling of the edges by real numbers. Equivalently, you may think of each member as simply a vector whose coordinates are indexed by the edges of the graph. Yeah. All right. And some notation. We are going to have a bunch of notation. For a vector x in the edge space, we mean the value of the coordinate indexed by that edge. Right. So that's just the yeah. All right. And the support of a vector, I guess everybody knows, the support of a vector is simply those coordinates where it is not 0. Right? Is simply the set of all edges such that x of f is not equal to 0. Yep. Alright, and one more thing. You can probably guess what it is, but I will still define it in a slightly more strange way. So what do you think is x of capital F, where f is a subset of the edges? No, so the vector is given to you. I just want to know what x of capital F is. I just want to define it as a particular value. Supposing I put half on all the, this is an example. Supposing this is my graph and I put half everywhere. on these edges, and the edges where I don't put anything is 0. If I don't label it, I mean it's 0. Now my question is, supposing capital F is this set. Well, it happens to be a perfect matching. What is x of this pink set? Sum of x's. Exactly. Right. So we're going to put it as 1. Right? Okay. So one way to define it is to do it the following way. We'll find this notation useful. So for any set of edges, for any subset of the edges, its incidence vector of this set is simply you put 1 wherever the edge is included and 0 wherever it is not included. So it's basically the vector, it's 1 if E belongs to F and otherwise it's 0. Right? So therefore the pink perfect matching corresponds to the vector that has 1s in these entries and 0s everywhere else. And now one way to define x of f is simply the dot product of x with the incidence vector of f. Right? So this is just x times the incidence vector of f. What is the notation? Okay. Yeah.
We can't do x is a set.
X is a vector.
Oh, that's support of it.
Yes. Yes. X is a vector here. Right? It's an element of the edge space. So you can think of it as a labeling of the edges. And now x of f is simply another way to write it is of course just sum over all edges in f, x of f, but observe that this is equal to this. Yeah? Right. Right. So in this example, if my vector x is the one in white color, then x of capital F, where f is the pink edges, is equal to half times 1 plus half times plus 0 times 1 plus half times 1. Yeah? Yeah? Okay? Alright, so that's some basic stuff with notation that we will need. Alright. Now let's talk about the perfect matching polytope. We can view every perfect matching as a 0, 1 vector. Yeah? So now what we can do is we can consider the geometric object that is created by all possible convex combinations of perfect matchings. And that is what is called the perfect matching polytope. And it lives in the edge space. Right? The edge space is some creature in high dimensions, depending on the number of edges of the graph. The polytope lives there. Right? It need not live in 2 dimensions or 3 dimensions because the number of edges may not be 2 or 3. So yeah, it lives in some higher dimensional space. But that's okay. We can still do math on it. So we will. Right? So so the notation I'll be using is directly from Lucchesi-Muti. I typically use PMP of G. I will still use the abbreviation PMP for perfect matching polytope. But the notation I'll go with Lucchesi-Muti. They use poly of G. It is a convex polytope. in where G is your red graph in its n space. In particular, it is a set of all convex combinations of perfect matchings. So if I let script M be the set of perfect matchings of course, when I want to specify a graph, I will write script M of G, but in general, let's say my graph is G, script M is a set of perfect matchings, then this is basically the perfect matching polytope is simply all vectors in the edge space of this graph that can be written as convex combinations of perfect matchings, such that X is a convex combination. I will define convex combination just to refresh of members in script M. This is our set. Let's do an example. Okay, let's do one example. Same graph. There are 4 perfect matchings in this graph, as we have discussed in the past. What I can do is I can take the perfect matching. Observe that this edge belongs to 2 perfect matchings. Either I take these 2 edges or I take these 2 edges. If I take those 2 perfect matchings, multiply the first one by half, well, multiply the vector corresponding to the first one by half, and multiply the vector corresponding to the second one by half, and I add them, you get the following vector. You get 1 over here, and you get half everywhere here in this 4 cycle, and 0 everywhere else. Whenever I don't write, I mean 0. So this is a vector that is in the perfect matching polytope of this graph, because I can write it as a convex combination of perfect matchings of this graph. Right? Of course, I should say not actually of the members of the incidence vectors of members in, yeah, right. So I have to take, I'm viewing each perfect matching as a vector. So we'll keep using these viewpoints interchangeably. But technically speaking, I should say the incidence vector of the perfect matching. But I may sometimes just say perfect matching. So, yeah. Is it okay? Yes, good.
So that figure, that why it is 0 times 1?
No, so here I was explaining this notation. I was explaining this notation where I am given a vector and I am trying to evaluate that vector at a subset of the edges where we are defining it. So the definition is just this. Right. So the set F here is the pink edges. The vector X is the white colored numbers you see. And so X of F is simply half plus 0 plus half. That's what it is. Yeah? Okay? Good. Thank you. Any other questions, concerns? Okay. Alright. So, okay, so let me just remind you quickly what a convex combination is. Anybody wants to remind the others what a convex combination is? So it's a linear combination, right? Everybody knows linear combination, yeah? And with some additional properties. The coefficients add up to 1 and they should be in the interval 0 to 1, right? So that's what, yeah. Non-negative is enough because they add up to 1. Non-negative along with that will imply, yeah, that's it. So, yeah, so recall that basically it's just if my vectors are labeled 1 up to r, it's just lambda I times xi right? So each xi is a vector here. Don't confuse this with x of e. That's different. That's a different notation, right? Each xi is a vector here, and here what we want is we want all the lambdas to be, yeah, okay, I can just write all the lambdas are at least 0, and the sum of the lambdas is equal to 1. That's what a convex combination of x1 up to xr. So this is what you're allowed to do, right? And of course, geometrically it makes a lot more sense. So if you're thinking about 2D, if I take 2 points in 2 dimensions, right, in R2, then the convex hull, the set of all convex combinations, will simply give you the line segment joining these 2 points. If you take 3 points in R2 that are in general position, not collinear, then you will simply get the triangle, the unique triangle, whose corners, also known as extreme points, are these 3 points. Right? If I give you 4 points, well, if they're in general position, then you will simply get a quadrilateral, a convex quadrilateral, with those 4 points as the extreme points. However, what can happen is maybe one of the points is contained in the triangle formed by the other 3. Well, then the convex hull is simply this. This point is in the interior. Right? Whatever that means. Geometrically it's clear. Okay? So that's basically what the convex hull looks like. And it's basically the set of all, yeah, so did I say, yeah. So the convex combination of members in a certain set is also called the convex hull of this set. Of course, technically I should say the incidence vectors of the perfect matching, but I'm just saying perfect matchings. Yeah? Okay? Alright. Okay, so now let's talk a little bit about convex polytopes. Yeah, so this is sort of a refresher on very basic polyhedral combinatorics. That's what this is. But of course, our main focus is going to be geometric objects related to perfect matchings. And the first such creature we will study is the perfect matching polytope. Right? But then we will also see some other creatures during this course. Okay. Okay, let's see. Are there any questions or concerns so far? Is the notation okay? Any confusion related to the notation? Yeah. Yes. Right. So x is my vector. Right.
We are looking at the value of a particular edge.
Exactly.
Okay.
Exactly.
Then
Right.
you choose the pink edge. F there.
Mm-hmm. So for the vector x, what is x of e for this edge?
1 by 2.
It's 1 by 2. This one?
No,
0. And this one is 1 by 2. Yeah. Yeah, so this drawing is kind of explaining 2 different things, but then it's also relating them by defining this. Okay, good. Any other questions or concerns? Okay, so let's let me make some space. Okay. Yeah, maybe this one should be given to CS office. It's completely useless. So a convex polytope is any subset of Rn Euclidean space if it is the convex hull of some finite subset of points. Finite subset of Rn. And let's remind ourselves what a convex hull is. The convex hull is simply for a given set, for a given finite set, it is a set of all convex combinations of this set. Right? Okay, let's do a quick example. And also let's just make sure we are okay with what a convex set is. You can think of the set being in Rn, if you like. Anybody? What's a convex set? If it is closed under taking convex combinations. If I take any set of points in my set, all possible convex combinations of those points should be in the set. That's why we call it convex. Right? Another way of thinking about it is you can actually think of 2 points at a time. That actually suffices. You can take 2 points, then if the 2 points are in the set, then the line segment joining them should also be in the set. Of course, here we are referring to line segment, possibly in higher dimensions. Right? Okay. Right. So, closed under, yeah, I'll just write this, closed under convex combinations. For example, in 2 dimensions this is fine, but what about this? Something like this. This is not convex, right? Because you take this point here and this point here, and now there are points that are convex combinations of these points, but they are outside the object. So that's not convex, right? And can anyone give me an example of a convex set that is not a convex polytope? What would be a convex set that is in R2? I want to draw it. Circle. A circle is a convex set, everybody agrees. A circle, if drawn well enough, hopefully, is a convex set, but it is definitely not the convex hull of finite number of points. You need all the infinite points in the boundary of the circle in order to, then it's not convex polytope, right? Okay, so this is not a convex polytope, convex set, but not a convex polytope. Yeah. All right, and let's also talk about extreme points. I used the word extreme points earlier. Let me define it formally. Anybody? What's an extreme point of a convex set? For example, in this triangle, what do you think are the extreme points? How many? 3? Yeah, that's right. So, well, so we all know from a very young age what the extreme points of a triangle are. We call them corners. Let's define them formally. So what is so special about these points that is not true for other points? Any other point can be written as a convex combination of other points of some points, but that is not the trivial convex combination. Trivial means the point itself multiplied by 1 plus nothing else. That's okay, but Right? But it cannot be written as a non-trivial convex combination of any other points. I won't define non-trivial, you get the point. Or maybe I'll just define it as it is here. Yeah. So an extreme point of a convex set S it's any point that cannot be expressed as a convex combination of distinct points in S. As a proper convex combination, proper takes care of that trivial thing. As a proper in the same set, right? Whereas if you take any other point in a triangle which is not a corner of that point, for example, I can take a point on this edge of the triangle, then I can write it as a convex combination of these 2 points, assuming my drawings are accurate enough. Right? It's just half times this point plus half times this point. If I take a point in the interior, well, that's very easy. Just draw some line segment around it, and it is half times this point plus half times this point. Right? That I cannot do for the extreme point. Another way to think of it geometrically is if you try to draw any line segment that passes to the extreme point, but the line segment is completely contained inside the convex set itself, then you will basically fail. So the point, if I try to draw a line segment which is not just a point and it contains the corner as an interior point of the line segment, then the line segment will definitely go outside the object. That's another way to think of it more geometrically, right? So, anyways, it's basically the same thing. Because what is a line segment? Well, it basically tries to mimic this as a convex combination of 2 points. Right? Okay. Good. Alright, what else? There are a few more points I have written down. I just want to go through them quickly. Every polytope, so remember how we defined a polytope? We defined it as the convex hull of some finite subset of points in Rn. Right? For example, if I take 3 points that are in general position, I'll get triangle. If I take 4 points, I may get a triangle if 3 of them are non-collinear, but the other one is contained inside them. Or I may also get this fellow. But the point is, every convex polytope is actually determined by its extreme points. Every convex polytope, if I want to describe a convex polytope to you, I can simply give you the extreme points of that convex polytope. And that actually determines the convex polytope. Right? Okay, so that's one point. And it is basically the convex hull of its extreme points. That's one way to think about it. Right? One more point. A convex set need not actually have extreme points. This one, for example, the circle, it has extreme points. But in general, a convex set need not have extreme points. Can anybody give an example of that?
The entire space.
That's true. The entire space does not have extreme points. You can take Rn, that is a convex set, that has no extreme points. Okay, now give me a proper subset. Yeah, that works. Now give me a proper subset in R2, let's say. Open. Exactly. Take the circle and remove its boundary. That is a convex set. But now it has no extreme points. Right? So if I remove the boundary, then I still have a convex set, but now there are no extreme points. Because I can get arbitrarily close to the boundary. You get the point. It's an open set. Right? Okay. Good. Alright, so these are some things. Yeah, and one more point, a polytope may happen to be the convex hull of two different finite subsets. For example, this triangle is the convex hull of these 3 points. It is also the convex hull of these 4 points, if I put a point inside it. So, a convex hull, a convex polytope could be the convex hull of two different sets. But what is interesting is that the extreme points define the convex polytope. Right? Okay, good. Alright, so I think that completes all of this stuff here. Okay, good. So while we're discussing all this, well, we're going to talk about the perfect matching polytope. So it's a good idea to have some grip on the polytope itself, on what a polytope is. Okay. So perfect matchings and matchings in general have a very, very long standing history and connection with combinatorial optimization. Right? It's not just structural graph theory, there are other areas of mathematics that have studied perfect matchings and related objects extensively. And one such subject is combinatorial optimization, which is also closely related to polyhedral combinatorics, where the focus is more on the geometry, whereas in combinatorial optimization, the focus is more on optimization problems related to these geometric creatures. Right? And one thing that the optimization folks are interested in is they want to write down a system of linear inequalities that capture this polytope. Because if they can write down a system of linear inequalities, then they can throw their optimization machinery on it and make some progress. For example, if you have a graph with, let's say you have a matching covered graph, it doesn't matter, with cost on the edges. And now you want to find a minimum cost perfect matching. Well, that's an optimization problem. Yes, you want to find a perfect matching, but not just any perfect matching. You want a minimum cost perfect matching, where the cost of a perfect matching is the sum of the cost of its edges. So if you want to solve this kind of optimization problem, it would be nice if you could first model this as an optimization problem, which typically requires inequalities. In this context, linear inequalities. There is also more fancy optimization, but we won't go there. We will stick to linear. Okay. But that raises a fundamental question. Given any polytope, remember a polytope, convex polytope. Of course, when I say polytope, I mean convex polytope. I'll generally just say polytope. Right? So it's a convex hull of some finite subset of Rn. Let's think about the perfect matching polytope. Given any graph G, you can assume it is matching code if you like, or you can just assume it has a perfect matching. Even that doesn't really matter. The number of perfect matchings is finite. It may be large, it may be exponentially many for all we care, but it is a finite number. Yeah? We are dealing with finite graphs, of course, throughout this course, as in life. Okay. So, the number of perfect matchings is finite. Therefore, you have a finite set of vectors in R to the E, one vector corresponding to each perfect matching. And therefore, if you take their convex hull, you will get a convex polytope by definition of convex polytope. Okay. What is not immediately clear is that for this polytope, there is a set of linear inequalities such that the solutions to that system of linear inequalities, are exactly the points in the polytope, and vice versa. That is not immediately clear. We will not prove that in this course. That's apparently a theorem of Weyl and Minkowski. I'll state in a bit. So the theorem basically says that given any convex polytope, there is a system of linear inequalities for which these are actually equivalent. A point belongs to the polytope if and only if it is a solution to that system of linear inequalities. Okay, and that is a theorem we'll assume, similar to how we assume the Jordan curve theorem when I teach STT. Right? So that's not going to be proved, but I need to give you the necessary context. Okay, so this is fine. Maybe let me get rid of this. Okay. But before we state the Minkowski-Weyl theorem, let me just go through some basics related to linear inequalities. So, What's a hyperplane? Well, in R2 it is very easy. Take any linear equation, it's a set of solutions. It's basically just a line in R2. Right? And now we generalize it. It is a set of all solutions to some linear equation in Rn, where of course all AIs are not allowed to be 0. Because then you won't get a line, then you'll get the entire, if all AIs are 0, then you simply have 0 equal to B, which is either the whole set or nothing. So that's, yeah. So long as at least one of the coefficients is non-zero, what you have is a linear equation, and the set of solutions is what we call a hyperplane. In R2, it's just a line. In R3, it will be a plane, and so on. Right? Okay. But what is interesting is if you put a less than equal to or a greater than equal to, then in the R2 you will basically get the line along with all points on this side, or you'll get the line along with all points on the other side. Okay? So that's what we call a half space. It's a set of all solutions to the same thing, replace it by less than equal to. Yeah. Of course, you could write greater than equal to, but then you just multiply the coefficients and you get a less than equal to. So it doesn't matter. Okay. In fact, I think Lucchesi-Murthy actually use, doesn't really matter. I'll go with greater than equal to because that is what we will use in the perfect matching polytope. It's equivalent. And observe that a hyperplane is nothing but the intersection of two half spaces. Let's just draw. Supposing this is my R2 and this is some, let's see, let's say I consider this line. Right? This corresponds to some linear equation. You can figure out this is 0, 1 and this is 1, 0. You can figure out the equation. This is your hyperplane corresponding to that equation. And if you put a less than equal to, you will get all points including the line segment, including the line, and everything on the left of it as per my arrow. And if you put a greater than equal to, you will get the other side including the line. And if you intersect these two sets, you will get exactly the line. Right? Which makes sense because it's simply the intersection of everything that satisfies the greater than equal to and less than equal to. So that's what it is. Alright. What is not too difficult to see using the definition of convexity, I suggest that you try it out yourself, is that half spaces and hyperplanes are convex sets. Right? That's not difficult to see. Yeah, work it out if you're not used to these things. Both of these are convex sets. Yeah. Make sense? Yeah. Okay. And another point that is worth noting is if you take the intersection of two convex sets, what you get is again convex. Think about it. It's not too difficult to see. If you take the intersection of two convex sets, you get a convex set. Right? In fact, if you take the intersection of any number of convex sets, you will get a convex set. By the same argument goes through. Right? You can take two at a time, of course, but right. Okay. Intersection of any number of convex sets
think we should have finite this.
Finite is important?
Yeah, because you can take all the tangents of the circle then I mean you can define half spaces using the tangents of the circle such that the intersection is the circle itself.
Then convex, no?
Oh, convex?
Yeah.
Oh, you didn't say polytope.
Right. Yeah, no, I'm not relating to polytopes yet.
Okay.
So intersection of any number, even infinite number of convex sets, is still a convex set. But yeah, we don't really care about infinite. It's just any number of convex sets is convex. Think about this. All of these are easy DIYs. They're not difficult. This is a DIY. Half spaces and hyperplanes are convex. Intersection of any number of convex sets is convex. Is also a DIY. They are not actually difficult. It's just a matter of getting used to the definitions. In fact, doing them yourself will help you more than my telling you why it is true. Okay. Good. And therefore, it follows that the set of all solutions to a system of linear inequalities is a convex set. Because every inequality, the solutions correspond to a half space, right? That is a convex set. And now I have a system of linear inequalities. So I'm just taking an intersection of bunch of convex sets. So therefore, yeah. Let's just write down. Therefore, it follows from all of this that the set of all solutions to a system of linear inequalities. Here, when we say system of linear inequalities, we require the number of inequalities to be finite, which I think is standard definition. To a system of linear inequalities, is a convex set. So we have two types of convex sets that we have discussed so far. We have discussed polytopes. Let's recall what a polytope is. Now we are relating the two things. Convex polytope is simply any set in Rn that is a convex hull of some finite subset of Rn. Right? That's what a convex polytope is. Right? And this is of course convex by definition because we took all convex combinations of the given points. Therefore, it is closed under convex combinations. That's literally how we defined it. Right? Then we have another type of convex set, which is a set of all solutions to a system of linear inequalities. And the reason this is convex is because of what we discussed here. It is simply the intersection of a finite number of half spaces. Half spaces are convex. Therefore, it is a convex set. Yeah. What is really not immediately clear is why these two types of convex sets are related. And that turns out to be what Minkowski and Weyl proved, that every polytope is the set of solutions to a system of linear inequalities and vice versa. So this is the Minkowski-Weyl theorem. I have no idea how it is proved. I might have seen it once upon a time, but I have no memory of it. Every polytope, by which I mean convex polytope, is the intersection of a finite number of half spaces and therefore it is a set of solutions to a system of linear inequalities. And thus it is the set of solutions to a system of linear inequalities.
I mean, the polytope consider every side as a line. I mean, extinct as a line, and those half spaces, the intersection will be the.
Right, I agree. That is how I would think about this. What is not immediately clear to me is this geometry that you seem to be assuming from the definition.
Yeah.
Right, the definition is just the convex hull. Of course, we are thinking of some creatures in R2 and R3, which is where our imagination kind of stops, at least mine does. Right? And yeah, it seems that it should be just there should be some edges or sides, and you just take an inequality corresponding to each side. But yeah, we never really proved that is what it looks like. But yeah, I agree that intuitively that makes sense. Yeah. Yeah, and if you actually give me a polytope, that is exactly what I will do, right? What we will do is, if this is the given polytope, we will just consider this line, the corresponding half space, this one, and this one. And now I will give you the system of linear inequalities. There will be 4 inequalities, and the intersection will be exactly this set. Yeah. But still, it's not immediately clear. Without having more geometric intuition and knowledge, I don't know how to actually sit down and prove this theorem. That's not very clear to me. But yes, should be something. There should be some geometry in there. Yeah. Good. Okay. Or maybe it's just algebra. I don't know. Or maybe there are multiple proofs. But anyways, the point is, what's the point of all of this? We are going to assume this theorem. And because this theorem applies to any polytope, therefore it applies to the perfect matching polytope. Therefore it follows that for the perfect matching polytope, there should be a system of linear inequalities such that a point belongs to the polytope if and only if it is a solution to that system. Right? So it follows immediately from this theorem that there should be a linear inequality description of the perfect matching polytope. And this was a major open problem back in the day that was finally solved by Jack Edmonds in 1965. Jack Edmonds gave a complete description of the perfect matching polytope of any graph. Right? And Edmonds' characterization of the perfect matching polytope is something that we will see a proof of in the upcoming lectures, including today. Let's see how much we get done today. Yeah, so that's where we are going. But sorry, this was a long story to explain what we are doing. Yeah. Questions, concerns? Hmm. 3:20. Maybe this is a good point to take a short break, and after the break we actually talk about the perfect matching polytope, right? Enough of just polytopes and convexity. Let's focus on perfect matches. Thank you.